Hello everyone, we were doing the chapter Gaseous State and Thermodynamics. We have discussed all the concepts that are there in this chapter, and we were discussing some questions based on PV diagram in the previous lecture. In this lecture we will do some miscellaneous types of questions that would use all the concepts that you have learned till now, and we will learn one or two new concepts through questions only. Okay, so we will begin with some questions, and during those we will understand what are the new things we didn't do earlier. Okay, so question 1 says that a flask of 2-liter volume provided with a stopcock to prevent the gas from leaking, basically contains oxygen, that is O2, at 300 Kelvin and atmospheric pressure, that is nothing but 1 atm. Okay, the system is heated to a temperature equals to 400 Kelvin with the stopcock open to atmosphere. Right? The stopcock is then closed and the flask is cooled back to the normal temperature, cooled back to the initial temperature, that is 300 kelvins. Okay, now you have to answer is basically final pressure of the gases, that is final pressure of O2 in flask, right? And the second is how many grams of O2 lost in the flask, right? How much of the O2 is lost in this process? So first of all, let's try to understand what is happening in this question. Let's say this is a flask that we have. It has O2 in it at 300 Kelvin and what atm pressure? This was the initial scenario, right? And there is a, let's suppose, stopcock over here. Then it was heated to 400 Kelvin, and this process took place when the stopcock was loose, as in the gas was allowed to move out of the container. That means the pressure was maintained 1 atm, right? The moles decreased. For, let's suppose that moles initially was N1, finally N2, right? Now then the stopcock was tightened, right? So in this situation we have O2 still at 1 atm pressure and 400 Kelvin. So let's try to first of all calculate how many moles are present in the first scenario and how many moles are in the second scenario. So first of all, as the obviously the volume has also remained same. Volume was 2 liters over here as well, and still it has 2 liters, right? So the equation is PV is equal to N1 RT for the first case. Similarly, PV goes to N2 RT for the second case. T1, T2. Temperature has changed, moles has changed, nothing else has changed because the pressure is both the time 1 atm, volume has been remained constant. So we can say that N1 T1 is equal to N2 T2, right? So we can say that is the moles in the starting into temperatures in the starting was 300 Kelvin is equal to N2 into 400 Kelvin, right? So 2020 cancelled out, which gives us N2 is equal to nothing but 3 by 4 N1, right? So this is the relation that is given to us by the given conditions, that it is taken from 300 Kelvin to 400 Kelvin under the open stopcock condition, right? So which says that almost one fourth of the gas of O2 has been lost, right? Okay, so let's try and calculate the final pressure. The initial, if we try to find out the moles in the initial condition, or we can directly relate it like this as well. The pressure initial was given to us as 1 atm, right? In the final question, that also is 1 atm. So 1 atm into volume of the container, that is 2 liters, equals N2 we have to find out into 0.0821 into temperature, which is 400 Kelvin. So which gives us the value for N2, which is nothing but 2 upon 400 into 0.0821, which is nothing but 2 into 10 raised to power 4 upon 821 into 400, which cancel out 2 zeros from here, gives us 50 upon 821 moles, right? So these are the moles in the final situation. Now the other thing that is happening is basically so using this we can find the N1 moles also. N1 is nothing but 4 by 3 into N2, right? So it would be 4 by 3 into 50 upon 821, right? So loss of O2, so the loss of O2 can be found out as N1 minus N2 into the total mass of O2, that is nothing but 32, which gives us the value 0.6504 gram. That is, this much oxygen has been lost, right? Now we have to find the final pressure of the O2 in the flask. Now to find the final pressure, what we are doing is, the container was with a fixed volume was taken from 400 to 300 degrees Celsius. So basically this process is nothing but saying that volume is fixed. It is basically isochoric process, as volume is constant. So P1, so P is proportional to temperature basically. So P2 upon T2 is equals to P2 upon P3 or P final upon T final, right? So pressure was given to us as the value 3 by 480, 1 atm, and the temperature given to us in the final was 400 kelvins. Now it is brought back to this initial condition with a temperature 300 Kelvin, which gives us the value of final pressure as 3 by 4 of atm. So what was substantial about this question is, you have to realize that the gas is being taken from 300 to 400 degree Kelvin in the open stopcock condition. Due to that, some gas would move out of the container, leading to the decreasing in the number of moles of the gas. Thus the pressure would remain constant, that is equal to the outside atmosphere pressure. Okay, so this was a different type of question from what we have done till now, because it had a change in the total number of moles. Till now we had done various type of questions in which we didn't involve the change of moles in it. Let's do another question which has a tube closed at one end containing a mercury column of 15 centimeter length inside it. The length of the air column trapped between the closed end and the mercury is 40 centimeters when the tube is horizontal. Okay, now you have to find the length of the air columns in the different conditions. You have to find the length of the air column in two conditions. The first being the tube is made vertical with open end downwards, and the second being the tube is kept inclined at 60 degrees Celsius, or at 60 degree with a vertical. With open end downwards. The additional information given to us is basically the pressure of atmosphere is equals to 75 centimeters of Hg. Right. So first let's try and understand what the question is trying to say. Basically you have a test tube like structure. When it was kept horizontally, you had a mercury column in it, right, and the air column. The length of the mercury column is given to us as 15 centimeter. Okay. So there is a mercury column like this. And earlier there was, first when this mercury would have been inserted into the test tube, there would have been air in it. So when you drop the mercury in it, the mercury will flow down till the point when the pressure exerted by the mercury is equal to the pressure exerted by the gas on the mercury. So when these both forces get equalized, then the motion of the mercury stops. So basically when the test tube is kept in the horizontal position, you have the air column as 40 centimeter, and then there is a column of 15 centimeters of mercury, right? So this was how the forces got balanced in the case of horizontal situation. Now what you have to find out is basically if the test tube is inverted, basically the open end downwards, then what would be the length of the air column, right? That you have to find out. And the second part says that the test tube is a bit tilted, making an angle of 60 degree with the vertical. Now what would be the length of the air column? That we are supposed to find. Okay. So let's suppose the cross section of the test tube be A. Right. Now we can say that if x x be the length of the Hg column, so we are saying that P1 P2 be the pressure of the two situations, right? Let P1 be over here and P2 be over here. Okay. And this situation where the length is given to be, here is y1, let's suppose, and here it is y2. Okay. Now we can say that the volume could be expressed of the test tube or the air column in the form of the length of the air column and the area of the cross section of the test tube. Similarly, V2 could be expressed as A into Y2. Okay, now we can see that we can equate the pressures on both the sides acting, that is the pressure exerted by the mercury and the pressure exerted by the gas. So let's assume that P naught is equal to atm pressure, which was in the case of the horizontal situation, right? So the mercury column was balancing it. So P naught was the atm pressure, right? So V naught was given to us as 40 into A, because 40 was the length of the horizontal air column. Now when it was tilted in the vertical direction, what would have happened is basically the forces would have got balanced. So to balance the forces, what we have is pressure 1 plus X equals to pressure, because in the vertical direction the force acting from downwards is nothing but the atmospheric pressure, because when the forces are being balanced, some force would be exerted on this mercury column by the air inside, and something would be its own pressure, but the only force opposing it is basically the atmospheric pressure. So P1 is of the air column, X is of the mercury, and P is applied by the atmosphere. So what we have is basically pressure outside is nothing but 75 mm of Hg, right? And similarly, first of all, let's write the second equation as well, which says that now the pressure would be exerted at an angle, right? So P2 would be the pressure exerted by the air column plus X, which is the mercury column, into 60 cos 60 equals P naught, right? And what we have the equation as P naught V naught equals P1 V1, because basically the gas has been expanding, just it has expanded. So it would follow the isothermal expansion law, that is the PV remains constant for an isothermal process. So what we have is the initial pressure was given to us as 75 mmHg, initial volume was 40 into A, it expanded to some volume that we have to find out, and the value of P1 is nothing but 75 minus 15, because we are given that X is 15 and this is 75 mm of Hg, into 40 into Y1, right? So Y1 is nothing but one sec, not 40 over here, my mistake. So it would be A into Y1. So A and A gets cancelled out. Y1 is nothing but 75 into 40 upon 60. So 2 by 3, 25. It becomes of the length of 50 centimeters. We had just used the thing that the total pressure is balanced by the external pressure, and the internal pressure would be exerted by the gas as well as the mercury. When the test tube is tilted, the component of the vertical component of the pressure would be balanced by the external pressure. Okay. So for the other case, we can have is the outside pressure is 75 into 40 into A, which is balanced by 75 minus 15 cos of 60 degree into A into Y2. So A cancels out. What we get is Y2 equals to 44.4 centimeters. So in this question, we discussed a brand new concept, which is based upon just we are treating the test tube in different positions, the vertical position, horizontal position, and the inclined position. In this, the basic concept was that when the mercury column gets stationary, it is because the forces acting on this has been balanced. The pressure outside and the pressure inside has been equalized. And in this equation, we have to consider the pressure exerted by the mercury itself, right? So let's try and do one more question, which is on the familiar concepts that we have learned earlier, that was the PV diagrams. So let's do another question, which says that a cylinder filled with fitted with a movable piston contains hydrogen gas H2 at a pressure of 3.5 into 10 raised to power 5 Newton per meter square. and at temperature 366 Kelvin. Right. H2 expands adiabatically. Until the pressure falls to 0.7 into 10 raised to power 5 Newton per meter square. So basically the gas is expanding adiabatically at the expense of its internal energy to attain a final pressure of 0.7 into 10 raised to power 5 Newton per meter square. The piston is fixed. The piston is then fixed and the gas is heated. Until the temperature is restored. The pressure final now found was 1.1 into 10 raised to power 5 Newton per meter square. You have to find the molar specific heat of hydrogen. Okay. Now let's try and first draw the PV diagram, because it's the best representation for the solving of these types of questions. So let's suppose the initial condition is plotted like this. A point, take it anywhere, that the gas was expanded adiabatically such that its pressure falls to the second value. So the initial value of pressure was given to us was 3.5 into 10 raised to power 5 Newton per meter square, and it fell to 0.7 into 10 raised to power minus 4, 10 raised to power 5 Newton per meter square. This was a adiabatic process. Now the piston was fixed after that. That means the volume was fixed. So the next process is isochoric process. And then there was an increase in the pressure to the final pressure 1.1 into 10 raised to power 5 Newton per meter square. Right. So this is the total scenario we are given to us. We have to find the molar specific heat of the gas. Okay. So for the given condition, the adiabatic process, we can say that the following equations hold, that is PV raised to power gamma is equal to constant, or TV raised to power gamma minus 1 is equal to constant, or we can say is T raised to power gamma or P raised to power 1 minus gamma is equal to constant. These three equations hold for the adiabatic process. Okay, so let's first of all mark these points as 1, 2, 3. So we can say that is the expansion in the volume took place in the initial condition. The temperature has also changed. So we can find the temperature at position 2 using the information we are given. Right. So what we are given is basically P1, which is 3.5 into 10 raised to power 5, T1, which is 366 Kelvin, P2, which is given to us as 0.7 into 10 raised to power 5, and the temperature T2 we don't know, that we have to calculate. Pressure 3 is 1.1 into 10 raised to power 5 Newton per meter square, and temperature 3 we need to find out. So using these equations, if we got T2 and T3, we can calculate the molar heat capacities, because we know the total energy required for the process as well as the change in the temperature. Right. So the process 2 to 3, which is nothing but a isochoric process, if we find the total energy required, we can get the value for CV. Right. So the isochoric process is governed by the law which says that P is proportionality to T. So P to T2 is equals to P2 upon T2 is equals to P3 upon T3. So we can calculate the value for T3 using it, which is P2 upon T3 can be given by P3 upon P2 into T2, right? Or we can do is the reverse method also, because we know the value that T3 has the temperature restored to the original value, that was 366 Kelvin, which gives us the value for T2 as P2 divided by P3, that is 0.7 upon 1.1 into 366, which gives us the value for the second position as 232.90 Kelvin. Now we have got the value for T2. Now using this we can find the pressure, right, which says that using the process 1-2, which was the adiabatic process. So the equation governing the relation between temperature and pressure was T1 raised to power gamma P raised to power 1 minus gamma equals T2 raised to power gamma into pressure 2 raised to power 1 minus gamma. So basically if we get the value for gamma, we get the value for CV and CP, both these. So if it have T1 upon T2 raised to power gamma equals P2 upon P1 raised to power 1 minus gamma. So which gives us the relation that 11 upon 7 raised to power 5 is equals to 1 upon 5, 11 by 7 raised to power gamma is equals to 1 upon 5 raised to power 1 minus gamma. If we take log on both these sides, what we get is log of 11 minus log of 11 by 7 into gamma equals 1 minus gamma into log of 1 by 5, which gives us the value for gamma as 1.39, which is roughly the value for, which is roughly 1.4, which is the value for our diatomic gas, that is 7 by 5. So if we are not given the value, the type of the gas, we can derive it using the expressions that we have for the processes and find the value of gamma, which can tell us which type of gas it was. So we can find the Cp, which is given by gamma into R upon gamma minus 1. So substituting the value for gamma, we get Cp as 29.58 joules per mole per Kelvin. And similarly Cv can be calculated by R upon gamma minus 1, which is equals to 21.28 joules per mole per Kelvin. So in this question, what was important was you have to realize that you don't know the type of gas it is, and to find the type of gas you have to analyze these processes and try to find out the value for gamma, and that can be calculated because we have the first process as the adiabatic process. So there is a relation between the temperature and pressure expressed in the form of gamma. So we can try to extract the value for gamma from that equation. So in this lecture we basically learned some new concepts, the new type of questions like involving the change in the moles of the gas, plus the second question was critical in terms of a new concept that at the column of mercury gets stable when the forces acting on it gets balanced. So the forces were expressed in the terms of pressure, and then the pressure was used in the terms of the various gas laws. So that's all for this class, and we had learned this completes our chapter gaseous states and